All right, strap in, everyone, because today we're going deep on Richard Feynman.
Ooh, Feynman.
Yeah, we're going to dig into some excerpts from his biography
Okay.
and really try to understand what made this guy tick.
Mm-hmm.
How he went from a kid messing around with radios to, like, cracking safes at Los Alamos and winning a Nobel Prize.
Well, what really gets me about Feynman is how his life just reads like some kind of, like,
An adventure novel.
yeah, adventure novel.
Oh,
But, like, beyond all the crazy stories, there's this, like, deep, like, thread of intellectual curiosity and this need to understand everything
Absolutely.
that drove him,
Yeah, and it all started, well, he was actually a late talker.
Oh, really?
Yeah, didn't say a word until he was, like, 3. But when he finally did start talking, it was with that thick New York accent.
It's like his voice was making a statement or something, like refusing to conform,
Yeah,
even in how he spoke.
Yeah, and his dad, Melville, totally encouraged that. Like, encouraged him to question everything.
Interesting.
Never take anything at face value. Would even, like, buy him books about nature and then be like, see, this is wrong.
Oh, wow, that's next level parenting.
Right.
For sure.
Totally fostered that skepticism, that drive to figure things out for himself.
Yeah, you can see that, like, in his early love for engineering and problem solving.
Oh, yeah.
Fixing radios, building a burglar alarm for his house.
Total tinkerer.
Yeah, definitely an ashtray.
But he didn't just want to take things apart.
Right.
He had to understand, like, the underlying principles. Like, he said when he was studying cats, he wanted, like, the map of the cat.
Oh, yeah. He wasn't satisfied with just the facts.
All
He
right.
had to see the blueprint, the whole system.
Totally.
And that way of thinking just, like, launched him academically,
Oh, for sure.
Like, at Far Rockaway High School, he was amazing at math.
Oh, yeah.
Taught himself all this advanced stuff, even came up with his own way of writing it down.
Yeah. Basically invented his own language for understanding the universe.
Pretty much.
It's crazy that one high school produced 3 Nobel Prize winners.
Wow, 3.
Yeah. Feynman, Burton Richter, and Baruch Samuel Blumberg.
That's wild.
Talk about a breeding ground for brilliance.
It really makes you think about, like, the environment that helped them grow. you know?
Totally.
And even back then, Feynman's approach was so different.
Oh, yeah. He aced the physics part of the Princeton entrance exam.
Aced it.
Perfect score.
Wow.
But then he, like, refused to join Mensa.
Mensa, why?
Said his IQ was too low. Joking, of course.
Oh, okay.
He wasn't about being part of some group with, like, a narrow definition of what smart is.
He wasn't afraid to, like, poke fun at the establishment, huh?
Even back then, no.
Yeah,
But, he still faced prejudice when he was applying.
really.
Yeah, some people were worried because he was Jewish.
It's sad that even, like, a genius couldn't escape that kind of bias.
Yeah, it was a different time.
For sure.
But Feynman, he persevered. Ended up at MIT,
Okay.
started in math, then electrical engineering, and then finally physics.
So he really bounced around a bit.
He did, but he didn't just cruise through either.
Oh,
Published 2 papers in Physical Review while he was still an undergrad.
as an undergrad.
Yeah, one was with Manuel Vallarta about cosmic rays. And then there's that story about how he got back at Vallarta for putting his name first on the paper.
Oh, yeah. What was that about?
So Vallarta, like, it was the tradition back then, listed himself as the senior author. Years later, Werner Heisenberg, in his book on cosmic rays, he ends with this line: "Such an effect is not to be expected according to Vallarta and Feynman."
Uh-huh.
And Feynman, never one to miss a chance to tease, made sure Vallarta knew about it.
That's so Feynman. Brilliant, but mischievous, always ready for a laugh.
Totally.
It's really interesting. He could be doing these super serious scientific things,
Yeah.
but still have this playful side.
Yeah.
Like, that's also obvious in his senior thesis,
The one about forces and molecules.
Yeah, that one, it laid the foundation for the Hellman-Feynman theorem.
Pretty impressive for an undergrad.
Yeah, very.
But what I find really interesting is that while he was doing all this complex science stuff, he was also dealing with some heavy personal stuff.
Oh, yeah?
His love story with Arlene Greenbaum it's heartwarming, but also so sad.
Yeah, it is.
They decided to get married even though they knew Arlene had tuberculosis and it was terminal.
Wow.
It says a lot about how much they loved each other.
It really does.
It's a relationship that really affected Feynman, both personally and professionally.
Yeah, I could see that.
And then, like, as if dealing with that wasn't enough, World War II starts.
Oh, right.
And Feynman gets recruited for the Manhattan Project.
Talk about a pressure.
It was a huge moment in history.
Absolutely.
And Feynman was right in the middle of it.
Wow.
At Los Alamos, he was working with some of the biggest names in physics.
Like who?
Hans Bethe, Niels Bohr, Enrico Fermi.
The best of the best.
Yeah, the brain power in that place must have been incredible.
I can only imagine.
And even then, his playful side still came out.
Oh, yeah. Like what?
He used to crack the combination locks on his colleagues' cabinets and desks.
No way.
Just for the challenge of it.
Seriously?
Yeah, and he even figured out how to make those IBM punch card machines, the ones they used for calculations, make them click in musical rhythms.
He just couldn't resist injecting some fun into everything, could he?
It's like he was a real-life Q from James Bond.
Uh-huh, yeah.
But instead of gadgets, it was equations that could change the world.
That's a great comparison.
And speaking of changing the world, Feynman's work on the Manhattan Project, especially his contributions to the Bethe-Feynman formula.
The one for calculating the yield of a fission bomb.
Yeah, that one, it had a huge impact on history.
It did.
But it came at a cost.
How so?
Arlene's health was getting worse.
Oh, no.
He was constantly traveling to see her, even borrowed his friend Klaus Fuchs's car to do it.
Fuchs. The one who turned out to be a Soviet spy.
Yeah, that's him.
It's kind of a creepy reminder of the Cold War and all that paranoia.
Sure.
Yeah.
And then, in 1945, Arlene passed away.
Oh, that's awful.
Feynman was devastated, but he kept working. Even witnessed the Trinity nuclear test.
Wow.
And of course, in true Feynman style, he claimed to be the only person who saw the explosion without eye protection.
Wait, seriously?
Ow.
He figured the truck windshield would filter out the bad radiation?
That's so typical of him.
Right.
Just thinking outside the box, questioning everything.
Totally.
It makes you wonder what was going through his mind, you know?
Yeah.
Seeing the start of the atomic age, something he helped create.
It must have been a lot to process.
Yeah, definitely.
So the war ends.
Right.
And Feynman's dealing with losing Arlene and the weight of what he was part of. He teaches at the University of Wisconsin-Madison for a bit.
Okay.
But decides not to go back after his time on the Manhattan Project.
Seems like Los Alamos really changed him. Yeah, maybe he needed a fresh start.
Possibly.
A new challenge.
Yeah, a new playground for his mind.
And that's where Cornell comes in.
Oh, okay.
They offer him a spot in their physics department.
A new chapter.
Exactly.
A chance to get back to theoretical physics.
Yeah.
And tackle some of the biggest mysteries out there.
And it wasn't just the science that drew him to Cornell.
What else?
He had connections there.
Oh.
Hans Bethe and Robert Batcher, who he worked with at Los Alamos, they both wrote him glowing recommendations.
So Feynman's at Cornell dealing with grief, the aftermath of the war, and now surrounded by these new intellectual puzzles.
Yeah, sounds like we're about to see some major breakthroughs.
I'm ready to hear about it.
We'll have to pick up the story in the next part of our deep dive.
Right, looking forward to it.
Last time we left Feynman at Cornell, right, dealing with like the loss of Arlene and these huge challenges of quantum electrodynamics.
QED.
Yeah, QED.
It's basically the theory of how light and matter interact.
Right, for those just joining us.
Yeah, it's like a cornerstone of physics today, but back then, it was a mess full of these inconsistencies and infinities.
So like a puzzle where the pieces keep changing shape.
Exactly, good analogy.
And this was the puzzle Feynman was wrestling with at Cornell.
He wasn't alone, though.
Right.
Lots of brilliant minds were struggling with it.
Mm-hmm.
And there was this feeling that, like, theoretical physics was falling behind.
Oh, how so?
The experimentalists, they were making all these crazy discoveries.
I can see how that would make the theorists feel like they had to catch up.
Totally. And that feeling, like being in the experimentalists' shadow, it was really obvious at the Shelter Island Conference in 1947.
This was a gathering of, like, the top physicists, right?
Yep. All trying to figure out how to move QED forward.
So did they have some big breakthrough, or is it more like brainstorming?
Kind of both.
Oh, okay.
They talked about the newest experiments.
Like what?
Things like the Lamb shift and the anomalous magnetic moment of the electron.
Those showed the problems with the old theories.
Yeah, they highlighted the gaps. But it also, like, kicked off this period of intense work.
How interesting.
Like Hans Bethe, he came up with a calculation for the Lamb shift, but it wasn't relativistic.
Meaning it didn't fit with Einstein's theory of relativity.
Right, and finding a relativistic version, that was the real challenge.
And this is where Feynman's, like, unique way of thinking comes in.
Exactly.
Yeah.
Feynman, he'd been working with these things called path integrals since his PhD.
All right.
He thought he could use them to get rid of those infinities in QED.
Ambitious.
He even tried working it out with Bethe. But their first attempts, the calculations weren't working out.
So, back to square one.
Not really. Feynman kept at it.
Stubborn.
He looked at his path integrals again, found a way to make them finite.
So, he got rid of the infinity.
Basically, yeah. And get this.
What?
His solution ended up matching Bethy's.
Really?
Even though they used totally different methods.
It's like they both climbed the same mountain, but from opposite sides.
Totally. And that made them think they were on to something.
But the real test came later.
At the Pocono Conference in '48.
Okay.
This conference is, like, legendary in physics.
Aw.
Partly because it's where Feynman first showed his alternative formulation of quantum electrodynamics.
Complete with those famous Feynman diagrams.
Those squiggly lines and arrows.
The ones everyone associates with quantum physics.
Yeah, it's crazy to think that they were once seen as so radical and confusing.
Right.
Back then, most physicists were used to working with these long, complicated equations.
Mm-hmm.
And then Feynman comes along with these visual representations of particle interactions.
Like a whole new language for the subatomic world?
Pretty much.
So did everyone love it right away?
Not quite.
Oh.
There was a lot of confusion, skepticism.
Who was skeptical?
Big names, Paul Dirac, Edward Teller, even Niels Bohr.
Wow, serious pushback.
They just couldn't grasp Feynman's diagrams or the math behind them.
That must have been tough, especially coming from someone like Bohr.
It was, but Feynman didn't give up.
Typical Feynman.
He knew he was onto something big, even if others didn't see it yet.
And thankfully, someone else did see it.
Yeah, Freeman Dyson.
That's the same Dyson who came up with the Dyson sphere idea, right?
The one and only.
Okay.
Dyson was a brilliant young physicist,
Mm-hmm.
and he got what Feynman was doing.
Interesting.
He realized that Feynman, Julian Schwinger, and Sin-Itiro Tomonaga.
3 different physicists.
Yeah, they were all working on QED, and they were all arriving at the same solution.
Even though their methods were totally different.
Exactly. Like, they were all speaking different languages, but
Yeah.
saying the same thing.
So Dyson was like the translator?
Yeah, the Rosetta Stone of QED.
Ah, that's a good one.
And what's amazing is he convinced Robert Oppenheimer.
Oppenheimer, the head of the Manhattan Project.
Yeah, that Oppenheimer.
Wow.
He convinced him that Feynman's diagrams were important.
That's huge.
Oppenheimer's support gave Feynman's ideas the attention they deserved.
Sometimes a revolutionary idea needs a champion.
Absolutely. And Dyson was that champion for Feynman.
So what did he do?
He published a paper in '49, added new rules to Feynman's approach,
Like what?
explained how to do renormalization.
That was the process for dealing with those infinities, right?
Yep, the ones that were causing all the trouble.
So Dyson basically made Feynman's ideas more understandable.
More palatable for the rest of the physics community.
And then Feynman's ideas started to take off.
Exactly. He published a bunch of papers in Physical Review,
Okay.
explained the math, introduced those Feynman diagrams to the world.
And the rest is history.
Those diagrams changed everything.
Yeah.
They gave physicists a visual way to understand quantum electrodynamics.
A whole new language.
Exactly. It's amazing how sometimes a simple picture,
Yeah.
it can be more powerful than 1,000 equations.
So Feynman's making waves in physics, but what about his personal life at Cornell?
It was a bit more complicated.
In what way?
He was still grieving Arlene,
Right.
and he always had this restless energy. Maybe he needed something new. He lived in unconventional ways, preferred warmer climates.
Yeah.
He even said he felt overshadowed by Hans Bethe at Cornell.
Even Feynman felt insecure sometimes.
It just goes to show even geniuses are human.
That's true.
They have the same emotions, the same desires.
Yeah.
And maybe that restlessness, that need for something different, is what led him to Brazil.
Ah, Brazil.
I've heard stories.
Me too.
It wasn't just a vacation, though, right?
No.
This was the Cold War.
Right. Tensions were high.
Feynman's friend, David Bohm, another physicist, he'd been accused of being a communist, had to move to Brazil.
Wow.
The FBI even questioned Feynman about his loyalty.
Seriously?
Yeah, someone close to him had raised concerns.
That's wild.
So all this political stuff going on,
Yeah.
Feynman decides to spend his sabbatical in Brazil.
In 1951, yeah.
He went to the Centro Brasileiro de Pesquisas Físicas in Rio de Janeiro.
A chance to experience a new culture.
Yeah, escape the Cold War, and of course,
Whack.
indulge his love of samba music.
Wait, seriously?
He even learned to play the frigidaire.
The what?
It's like a metal frying pan you use as a percussion instrument.
The guy who revolutionized QED was jamming on a frying pan in Rio.
It just shows how multifaceted he was.
Yeah.
A brilliant physicist, a playful prankster, a lifelong learner.
And someone who just loved life.
Exactly.
I think a lot of people don't realize that side of him.
Yeah, it's important.
It shows his endless curiosity, his willingness to embrace new things in and out of science.
And that openness, it would lead him to a whole new chapter.
A new chapter.
Yeah, move to Caltech, a new marriage, groundbreaking work on all sorts of stuff.
Sounds like we're about to get into some really exciting stuff.
Buckle up, it's going to be a wild ride.
Yeah.
Caltech, sunshine, new scientific frontiers.
Right, and it wasn't just research. He met Mary Louise Bell there, and they got married.
Oh, wow. Mary Louise Bell.
Yeah, she had a totally different background, like history of Mexican art and textiles.
It's interesting how Feynman was always drawn to people with such different interests. It shows how multifaceted he was.
Yeah, totally. Always thirsty for knowledge.
Absolutely.
But their marriage, from what I've read, it wasn't exactly smooth sailing.
Yeah, unfortunately not.
Their personalities clashed. They ended up divorcing in '58.
It's tough. Even brilliant minds struggle with relationships.
Yeah, for sure.
But through all that personal stuff, Feynman's work at Caltech, it was incredible.
Oh, yeah, he got into so many different areas.
Superfluidity, weak interactions, even the beginnings of quantum computing.
Okay, let's unpack that superfluidity first.
Okay.
This concept has always blown my mind. It's like liquid helium just decides to ignore the laws of physics and flows without any resistance.
It's like it becomes a ghost, slipping through cracks, climbing walls.
Exactly. It's bizarre.
Feynman loved that kind of stuff, the strange and counterintuitive.
Yeah.
He wanted to explain this using quantum mechanics, built on what Lev Landau had done.
So he was trying to connect the dots between what we see, the liquid helium flowing without friction, and the tiny world of quantum mechanics.
Exactly. And what he found was amazing.
What?
The superfluid, it was showing quantum behavior, but on a big scale.
Whoa. So the weirdness of the quantum world was like leaking into our everyday world.
That's a good way to put it. It's mind-blowing.
Did this work on superfluidity tell us anything about other areas of physics?
Like superconductivity?
Yeah, where materials conduct electricity without any resistance?
Well, Feynman's work didn't directly solve superconductivity.
Okay.
But it laid some important groundwork.
Makes sense.
The full explanation would come later with the BCS theory. But Feynman's insights into superfluids, they were key.
It's fascinating how these different parts of physics can be connected in ways we don't expect.
Yeah, like the universe is dropping hints.
And it's up to physicists like Feynman to figure them out.
Exactly. And Feynman, he was so good at connecting those dots.
Seeing patterns that others miss.
Yeah, that's what made it so special.
And speaking of connecting dots, he also did a lot to help us understand the fundamental forces of nature.
Right, the fundamental forces.
He worked with Murray Gell-Mann,
another giant in physics,
to develop the VA theory of weak interactions.
No, that's a mouthful.
It is. Basically, it explains how particles, like neutrons, can decay into other particles.
Protons, electrons, antineutrinos.
Yeah.
All that. It showed that the current in this decay, it's a mix of vector and axial currents.
Okay, hence VA.
Right, it was a big step in understanding the weak force.
One of the 4 fundamental forces.
Gravity, electromagnetism, strong force, and the weak force.
And they gave us a better picture of this fundamental process, particle decay.
A more complete picture, more elegant, too.
And then Feynman went after the strong force.
The one that holds the nucleus of an atom together.
Right, and that's where his Parton model comes in.
The Parton model, it was Feynman's way of understanding protons and neutrons.
Okay.
He said these particles, which people thought were fundamental, were actually made up of even smaller particles.
Like how atoms turned out to be made of electrons, protons, and neutrons.
Exactly, Feynman was saying. Maybe there's something even smaller inside.
But wasn't Gell-Mann working on something similar around the same time?
The quark model.
Yeah, that's it. Didn't those two models kind of clash?
There was some tension, yeah.
Okay.
Gell-Mann had also come up with the idea of quarks.
Right.
And at first, it wasn't clear if Feynman's partons were the same as Gell-Mann quarks.
So 2 brilliant minds, both coming up with similar ideas.
There may be a little bit of ego involved, too.
Even geniuses have egos.
It's true. Science is a human thing.
Yeah.
Collaboration, competition, it's all part of it.
But they figured it out eventually, right?
Yeah. Feynman's partons became a way to describe how quarks behave inside protons and neutrons.
So both models contributed to our understanding.
Each brought something unique to the table.
And were they proven right?
Oh, yeah, big time.
How?
Experiments at the Stanford Linear Accelerator Center in the late 60s.
Okay.
They showed that protons and neutrons really did have these smaller particles inside.
Just like Feynman and Gell-Mann predicted.
Pretty amazing how these ideas, these models from the human mind, can be confirmed by experiments that look at the tiniest parts of reality.
It's a testament to the power of both theoretical and experimental physics.
And how they work together.
Absolutely.
But Feynman wasn't done. His curiosity kept pushing him.
What was next?
He went after an even bigger challenge, quantum gravity.
The holy grail of physics.
Trying to combine Einstein's general relativity with quantum mechanics.
A problem that stumped everyone for decades.
Yeah, it's a tough one.
Did Feynman make any progress?
Well, he didn't come up with a complete theory.
Okay.
But he made some important contributions.
Like what?
He looked into gravitons, these theoretical particles that carry the force of gravity.
Interesting.
And he even started thinking about quantum computing.
Quantum computing, that futuristic stuff.
The same. Amazing to think he was already thinking about it back in the 80s.
Yeah, a true visionary.
But Feynman's legacy, it's more than just his research.
Right.
He was an amazing teacher, inspired tons of students with his Feynman lectures on physics.
Those lectures are famous.
So clear, so funny. He made complex stuff understandable.
In that quote, "What I cannot create, I do not understand."
It perfectly captures his approach to learning.
Hands-on, building, experimenting.
He wasn't satisfied with just theories. He wanted to see how things worked, get his hands dirty.
And that playful curiosity, it's everywhere.
From fixing radios as a kid to the Manhattan Project to nanotechnology, quantum computing.
But his dedication to truth and clarity, it went beyond science.
Remember his role in the Challenger disaster investigation?
Oh, yeah, that was huge.
He wouldn't accept vague answers, did that demonstration with the O-ring and ice water.
Showed everyone what went wrong.
It was a powerful reminder. Scientific integrity is important.
And having the courage to speak truth to power.
Feynman had both.
He was a fearless truth seeker, an inspiration to anyone who wants to question, explore, understand.
True original, a one-of-a-kind genius.
So as we wrap up our deep dive on Richard Feynman,
what have we learned?
What are the key takeaways?
Remember his curiosity, his playful approach to problem solving, his dedication to understanding the universe at the deepest level.
He showed us science can be fun and serious at the same time.
Rigorous and creative.
And that seeking knowledge is an adventure.
An adventure worth having.
Well said. And as Feynman said, the first principle is that you must not fool yourself, and you are the easiest person to fool.
Wise words.
So keep asking questions, challenge assumptions, never stop exploring this amazing universe.
And never lose that sense of wonder, that thirst for knowledge.
Like Feynman did.
He also said, the most beautiful thing we can experience is the mysterious. It is the source of all true art and all science.
That's a perfect way to end.
Until next time.
Keep diving deep